is CORDIScovery. Hello and welcome to this episode of CORDIScovery with me, Abigail Acton. Robotics is a swiftly changing field. Cheaper hardware is making research more accessible, and thanks to advances in AI, focus is now shifting from feats of physical dexterity achieved by expensive robots to building general-purpose robot brains in the form of neural networks. A recent breakthrough from the Massachusetts Institute of Technology is pushing the boundaries of robotic intelligence. By shifting away from traditional data training methods, MIT's researchers have set their sights on mimicking the techniques behind large language models like GPT-4. This novel approach promises to revolutionize how robots learn, adapt, and interact with the world around them. So what are the latest developments in robotics at home, at work, and in the fields? What can novel assistive tech do to help people live independently? Can robots help prevent injury at work? And how can biomimetics inform the design of future robotic systems? Our three guests, who have all received support from the EC's science funding programs, will talk us through their work to answer these and other intriguing questions. Mac MacLachlan is Professor of Psychology and Social Inclusion and co-director of the Assisted Living and Learning Institute at Maynooth University in Ireland. He's particularly interested in innovative technologies that are helping people remain independent for longer. Hello, Mac.
Hello, Abigail. Lovely to join you.
Lovely to have you. Arash Ajoudani is the Director of Human-Robot Interfaces and Interaction Laboratory at the Italian Institute of Technology. He's interested in physical human-robot interaction, mobile manipulation, and assistive and telerobotics. Hello, Arash. Welcome.
Hello, it's good to be here. Thank you.
Professor at the Dahlem Center for Machine Learning and Robotics at the Free University of Berlin, Tim Landgraf investigates the social behavior of guppies and bees in order to understand biological intelligence and refine artificial intelligence. Welcome, Tim.
Hi, Abigail. Nice to be here.
Great. Good to have you. Mac, I'm going to turn to you first. The SHAPES project aims to enable the large-scale deployment of digital technologies for healthy and independent living. One tool that the project has explored is the Compi 3 robotic assistant. Can you tell us what challenges robotics could help us to meet, Mac?
Sure, Abigail. Yeah, thank you. So I think one of the big challenges facing all countries across Europe are the demographic changes. So we have had very successful health systems within Europe, which means that we now have more people living longer. But there's also a demographic shift so that there are fewer people being born. And so if you put those two things together, what you have is a greater level of need, but a lower level of supply. So if we look, for instance, ahead to the year 2030, WHO estimates that there will be a 4 million shortage in the workforce. 58% of those will be nurses, 28% will be other health and social care professions, and 15% will be doctors. So the challenge is, how are we going to provide personalised healthcare to people in their communities, ideally in their homes, in the years ahead?
Yeah. So obviously there's clearly an imperative and you can feel almost that the clock is ticking. So can you tell me a little bit about the work that the SHAPES project did to make robots a more feasible option, please?
SHAPES stands for Smart and Healthy Aging, through empowering people by engaging in systems. And empowering is the key word in that acronym, because what we want to do is to give people technologies that allow them to live comfortably at home in their communities. But there's no single technology that can do that. Really, you need a whole array of different sorts of technologies. So some of these may be large data pools in the cloud. Other aspects may be sensors in somebody's home. And other aspects may be other forms of sort of data lakes or data mining. The key thing is that any piece of technology should be able to talk to all those other pieces of technology. So if you want to provide integrated services, integrated care, you want a robot that's able to communicate with the other information that's relevant to that person. So the SHAPES project sought to create, if you like, an ecology that looked at the technical demands of providing a robot, linking up to the other sorts of technologies available but then also the social demands and indeed the governance issues and ethical issues around data protection, privacy protection, and so on.
Okay, lovely. So can you tell us a little bit more about the Compire 3 robot, what it was able to do, and whether you have any feedback from users with regards to how they felt it helped them? It would be interesting to know, the impact of this robot in people's lives.
Sure, yeah, thank you. So we had, I think, 56 different partners in this project, and one of them was Compire Robotics. We're very pleased to partner with them as they're one of the leaders in this field. And their Compire 3 robot, which is something that sort of stands almost shoulder length, if you like. It's got a wider base and then narrows, and there's a human-like face at the top of it. And really what that does is a number of different things depending on the person's needs. So, for instance, it can be a conversational companion, answering questions or providing information to reduce feelings of isolation. On the other hand, it could be it could guide somebody's walking as part of a gait rehabilitation exercise.
Oh, so when you say a gait rehabilitation, you mean like frail walking to try and make someone walk in a way that's more stable and robust?
Yeah, exactly. And it can provide both support and feedback to them about how they're progressing there. Similarly, some people as they age may have cognitive problems, and Compire 3 can provide sort of medication reminders and monitoring. And it can look at sort of long-term adherence to medication. And then also, of course, you'll be aware that falls are a particular challenge for some people as they age. So another feature of Compire 3 is that it can sort of navigate somebody's living environment. So clearly, for some people as they age, they may have sight difficulties or hearing difficulties or cognitive or indeed mobility difficulties. And so the Compire robot can help in different ways for people to essentially retain their independence and again to live within their own community.
Super. And did you have any feedback from users? Have you heard whether people are finding it easy to interact with the robot, or do people feel reluctant to do so? What's the feedback on this?
Across the project, but also applying to Compire 3, people were extremely enthusiastic about technologies. And that's a really good question, because we often think that older people are a bit less open to new ways of doing things and new technologies. I think one of the things we found in this project is when you co-design and co-develop technology with people, and they feel that they have much more of a say into it and it's more relevant to them, then in fact they're incredibly welcoming of these technologies. And through the project, for instance, as well as the gait rehabilitation that I mentioned earlier, other features that were added to the Compire 3 robot include facial recognition and natural voice interaction with people as well. So they're key in that personalized service sense.
Yeah, to make people feel more relaxed around them and more accepting of them. This is excellent. So then, $60 million question. When can we start to expect to see robots in care scenarios like this? My mother is elderly and at home, maybe later in the future, this would be quite nice for her to have. What's it looking like with regards to uptake in the market?
I think there are already, robots providing assistance. If you look, for instance, in Japan, the social acceptance of robots, I think, is much greater. And so within Europe, we have an interesting challenge. It's maybe less the technical challenge of what a robot can do and more of the sort of social challenge in terms of feeling that a relationship, if you like, with a robot is an okay thing, that a robot is safe, a robot is something you can trust, and that overall that a robot can be a meaningful contributor to, enhancing your life and supporting your well-being.
Excellent. Thank you so much for telling us about your work. That's fascinating. What do you think that assistive robots will be able to do in 20 years' time, for example?
Yeah, so that's a very nice question. I mean, we can distinguish between assistive robots that are helping people with particular tasks that need to be done, and then companion robots, which really make people feel, well, that they have a companion, that there are others around, whether they are other people or other things that care for them and about them. And I think that distinction of crossing the mental barrier and thinking that a robot cannot just only care for me, but it can also care about me, is going to be very important for those companion robots. So I think assistive robots will do more in terms of more ways of assisting people, but I suspect that they will also take on more features of companion robots.
Excellent. Thank you very much. I'm reminded of that robotic seal that came out of Japan for people to help people with dementia and how...
Peru, yeah.
Peru, thank you. Yeah, that's right.
Yeah.
And how massively people loved it and accepted it and were happy to have it.
Absolutely.
Lovely.
Yeah.
Thank you so much. Yeah, super.
Thank you.
Arash, I'm going to turn to you. The Sophia project set out to develop a new generation of socially cooperative human robotic systems which can enter into direct socio-physical contact with humans to perceive, understand, and react to their distress or needs. Now, here we're shifting from assistive tech to look more at industry and the use of robots in that scenario. Your project has two main aspects. Can you tell us about the element to do with preventing injury, such as back strain, something that hangs over millions of workers and which has implications for long-term health and financial consequences? What did Sophia develop for that?
So thanks for the question, Abigail. Sophia wanted to address work-related health issues. So the alarming factor was in Europe, we have about 240 billion euros lost every year in lost productivity and problems associated with the all the insurances and everything that workers, the absenteeism, and all this is related mostly to work-related musculoskeletal disorders that the workers of today have to do repetitive or heavy tasks in manufacturing, in warehouses, in logistics. That is an alarming factor, which is really not really paid attention to. I think the biggest technological gap for this was today's monitoring systems that are looking into how people are performing their jobs in terms of ergonomics are quite outdated. They are mostly very, let's say, posture-based, that they are not really taking into account how external loadings and how different dynamic factors in the environment can actually influence the well-being of people and in general, the ergonomics of people performing their jobs. So our first really important goal was can we revolutionize this? Can we provide some new methodologies that in real time they can tell us how a worker is actually undergoing some fatigue in short or too long terms, and how these physical interactions can actually change the well-being of a person. So this was the first important, let's say, milestone for us to achieve.
Okay, thank you. So can you tell us a little bit about the wear robots? Where does somebody put them on their body? And how does that send data back to some system that can make a change?
Absolutely. So the wearable robots, we call them wearbots, were supposed to get all the necessary data to be able to build these, let's say, digital models and to tell us how the dynamic states in human articulation and human joints are changing. These wearable robots will tell us about the posture of the person, about the let's say acceleration and if possible, let's say some let's say muscular activities of people doing that. And why we tried to use wearable robots was that due to the privacy issues, we tried to minimize the use of cameras. And also in cluttered spaces, the use of cameras usually is not really easy to detect postures of people, especially, for instance, if you're imagining a person in between, let's say, pallets or inside a very narrow aisle of an airplane, which is trying to mount things. So the wearable systems not only preserve privacy, but also can give you meaningful data. But it comes also with some issues, of course, in terms of, sanitization and others.
Lovely. Thank you so much. So what, it straps on around the back, or it's something that straps on around the arms, or, I mean, where does it actually go on the body?
So it goes on important joints and important, let's say, key points of the body that we want to measure. Let's say some quantities that we want to elaborate and give some indication of the load. And these variable systems are not only for measurements, but also can provide feedback. We have some vibrotactile modality that tells a worker that, for instance, your shoulder is being overloaded. If you continue this way of working in such a way, you might you're posed to some issues in long term, and this feedback will be reduced if the worker can change the posture.
Oh, that's fantastic. So it's like a haptic feedback that buzzes you if you're doing something not so great, and the buzz gets less and less and less as you correct that position or whatever it is. I think this is wonderful. But it's not the only thing Sophia looked at. You were also looking at the notion of collaborative robots. Can you tell us a little bit about cobots, please?
Exactly. So cobots are basically collaborative robots that create synergies between humans, and they can perform the jobs. But what Sophia did differently was cobots were not only trying to focus on the task, cobots were also trying to improve human states in terms of ergonomics and in terms of physical and cognitive states. So we brought these models, digital human models, into the optimization and into the control frameworks of these collaborative robots. So these robots could reconfigure, could change the way they were doing, so that this new way of working with humans not only contributes to speeding up or making productivity better, but at the same time, it can improve the ergonomics of people working with it.
Okay, so I'm not quite sure I understand that. Could you give me a concrete example?
Yeah. So imagine a very simple example. A robot is passing you a 2-kilogram drill, right? Or any tool that you're supposed to work with it. So there are infinite number of places in the space that the robot can hand it to you, right? But there's only one, which is the most optimum in terms of workspace that you prefer to get this. And also it has the minimum impact on your body in terms of ergonomics, because each 2 kilogram or each gram that you add as an external load, it has some consequences in your joints, right? So if you multiply it to 8 hours per day and to 300 days per year, this will have really bad consequences. So the robots in this easy example will pass you the object with minimum impact on your health and maximum impact on your productivity.
That's lovely.
Yeah, this can scale to many, many dynamic and challenging tasks.
That's great. And your underlining of the notion of repetitivity is really important here, because absolutely it's something that builds and builds and builds. So the robot would hand me the drill to my hand in a way that was the best way for me to be receiving it rather than elsewhere or whatever. Super. So it's like fine-tuning the interaction. Right. Excellent. Thank you. And how is this working in practice? Have you had any pilot studies?
Absolutely. So we had 3 pilot studies. We also brought our technologies to Volkswagen. They were producing electric cars. We had a pilot study in the Netherlands. It's an SME. They were producing gears of 4 to 20 kilograms. We had a pilot study in Slovenia. They were producing machinery tools. So all these, they use different tools and let's say technologies developed by Sophia in terms of cobots, in terms of variable systems. We also developed some exoskeletons, wearable exoskeletons, single joint exoskeletons. All these through some really deep impact analysis, we understood that we are able with these technologies to not only maintain and improve the productivity, but we were able to improve significantly the ergonomics and well-being of people performing the same jobs. Obviously, if something can be automated, should be automated, but until we can automate everything, we need to go towards synergistic workstations where humans have all the dexterity and all the skills, and robots can start learning and getting this transfer of knowledge from human. Until then, robots can definitely improve productivity and ergonomics, and all our use cases showed significant benefits of using Sophia technologies in multiple aspects.
Fantastic. That's excellent. You must be very proud of that.
Absolutely, I am.
Yeah, I'll bet. Excellent. Thank you. And it's obviously a big team behind you. As you said, you were part of a consortium. Lovely. Does anyone have any comments or observations to make to Arash? Yes, Mac.
Yeah, it's really interested to hear in your work there, Arash. And I was just thinking, thank you, as you were describing it, to some listeners, it may seem like we're doing different things in that I'm working with people with functional difficulties, whereas you're sort of optimizing performance. But in another way, I think robots is helping us remove that divide, because in all contexts, it's actually about optimizing performance. And from my perspective, that's really important, so that people who may have functional difficulties can think about getting better at things than they've ever been, as opposed to just making up for a deficit.
Absolutely, Mac. Yeah.
Excellent. No, it's a good observation. Yeah, it does really directly overlap in that way. Thanks very much for that observation.
If I can comment on that,
please.
This is an excellent observation. Of course, when you build these digital models, of course, this can scale to healthy people to monitor if something can happen, something bad can happen to your limbs. But you can also scale it to people that come back to work after an injury. So you can make sure these robots adapt in a way that they're using the minimum the joints that have been injured, or elderly, or people with physical difficulties, so you can optimize the way the people want or best should work.
Yeah.
And this, as you mentioned really nicely, everything comes down to an optimization. And for that, we need models. And that's why our projects, I think, are contributing very well to this.
Absolutely. No, really great. And from such different angles. And I'm going to turn to Tim, who's coming from a completely different angle, because we've talked about people and how they can be assisted by robots in various ways. But I'm also interested in the use of robots in agriculture and biomimetics. In other words, the way we can imitate what's out there already thanks to nature. So, Tim, by studying swarm intelligence, Hiveopolis, your project, has developed the concept of a robotic dancing bee as part of a futuristic honeybee hive, helping pollinating bees to perform well in very challenging environments. So can you tell us a little bit more about biomimetics? What are biomimetic robots and how can they be useful, Tim?
So biomimetic robots, that, the name already gives it away. Robots that mimic biological templates like animals, plants even. And why they do that, there's a ton of different applications, right? So you could have like a legged robot that walks like a dog, and excels in rough terrain for a variety of purposes. Or you could have biomimicry because you want to integrate a robot into an animal society, an animal group. That's our case. Why would you want to do that? Well, I mean, you could, think of agriculturally used animals, so you can control or use those robots inside those groups to gather information on health or, other important aspects, how the group is doing.
Okay, so tell us a little bit more about Hiveopolis. So you developed the concept of a robotic dancing bee. What work did you do to model and replicate the performance of the bee dance? Perhaps maybe start by telling us what the bee dance actually is.
Yeah, so bees fly out, explore the environment for food and other resources. And if they have found something, they come back. And if that something is really valuable, they do something that we call the waggle dance. That is this very specific behavior that other bees observe. They follow that dance, basically, also, body to body contact with the dancer. And then they kind of learn where that forager had found the food or whatever resource. And they fly out. So it's basically communicating the location, direction and distance of that food source. And that's like from a basic fundamental science point of view, really interesting because those animals are super small, the brain the size of a pinhead. So how does it even work, right? So it's just like a symbolic kind of communication. So there's a lot of interest in understanding how that works and does it actually work? And if we then know how it works, we can obviously also use it. So that was the idea in Hiveopolis. So integrate technology into a beehive. And there's many, many things. And the bee robot, the dancing bee robot was just one part. But then use this technology to, on the one hand, learn a lot of, about the health and the status of the hive, but also use the robotic components to basically feed back information, to steer them to a healthier colony state. So tell them where they can find food. Or stop them from going somewhere where the food is maybe treated with pesticides.
Right. And so in the project, how far did you get with actually creating the notion of a dancing bee? Was it that you did the modeling and worked out, the programming behind it? Or did you get as far as actually developing a robotic dancing bee? How did this go?
We built so many different prototypes. I think I lost count.
I'm sure.
So we basically went into the project with already a working prototype. So in my PhD thesis a long time ago, I built a robot that could perform the waggle dance, but it was huge and clumsy and had to have a lot of manual control to basically do what it was promising to do. And so our goal was to minimize everything, put it in a standard beekeeper hive so that it actually could work without having to open it up, disturb the bees, because we wanted to help them, right? So that's the whole system, was to basically give back to the bees, because we hurt them by, using them like we do. We make them unhealthy and give them parasites and all these things. And so the goal was to give them back. And so our work was software development, modeling the dance behavior, but also minimizing all the different components such that, we can actually use them without opening it up. I think like outside robotics, especially what Mac is doing, but also what Arash is doing, it's so different from lab robotics. And, if there's animal stuff, wax and propolis and all these things stick together and they don't move anymore. And then there's like a whole bunch of different problems that you never think of in the lab.
No, that's a very interesting observation. Absolutely. So in practice, there are different contexts, of course. I was just wondering what the results were. Did you manage to direct the bees to certain places? And I noticed also there was something to do with weather forecasts. And I mean, was there, how was the information all cross-shared?
Yeah, in Hivopolis, it's not all about the bee robot. It's basically an array of different systems, from maps that basically collect different sources from different sources of information, like where was pesticide being brought on the fields, and where are other colonies that we probably should be kind of coordinating with. And so all this information is collected in these maps, and then we have different components like a honey harvesting module and like the dance flora module that could also stop dances and code dances, so see where they are going. And then everything is integrated. Human stakeholders are also sought to, participate in this, right? So give us information.
You mean farmers, for example?
Farmers, but also we call them hipster beekeepers.
Hipster beekeepers.
So those who have 1, 3, or 4 hives on their roof.
Like urban beekeepers.
Urban beekeepers.
Yeah.
Right? Everyone might benefit from this system. And so, the robot works more or less, mechanically. Is it as efficient and as useful in the actual world? No. There's a lot of research to be done. But yes, I think this project was defined in a very crazy kind of perspective. And it was clear from the beginning that it takes more than 5 years.
Oh, yeah, sure. But I mean, they all do. It's always just laying down the groundwork for the next stage. It's like building a brick wall. It's a layer of bricks and then you have to put the next layer on top. Absolutely fantastic. Thanks for explaining that so well. Excellent. Well, I have one final small question for you, Tim. If you could look down the line in 10 years into the future, for example, how do you see biomimetic robots evolving? If we do some blue sky thinking, where could we go with this?
Well, I mean, to be honest, I think the natural world is like a technology that is super far advanced. So we should probably be biomimetic most of the times. And we are not yet because we can't. Sensors are not as good, and actuators are not as, good, and battery life is slow, and materials are bad, and robots fall apart after 5 years and not 50.
Oh, they get sticky with honey.
Yeah. And so what I see is like an integration much deeper, and you can't see those sensors anymore, and more control over our environment to keep it healthy, to detect diseases early and all these things, right?
Yeah, excellent. Okay, thank you very much. Well, that's a positive hope for the future anyway. That's great. Well, listen, thanks to all three of you for sharing your time with us today. That was really super. And I particularly like the way that we looked at these various elements of robotics. So thanks very much, and all the very best with your researches.
Thank you so much for having me.
Thank you very much for having us.
Real pleasure.
Thank you. I think we should all have a waggle dance.
Yeah, we should have a waggle dance to celebrate. We should.
Absolutely.
Pointing people over to CORDIScovery online. Absolutely. Thank you very much, guys. Thanks for your time. Goodbye.
Okay, bye.
Excellent. Bye.
Bye-bye.
If you've enjoyed this podcast, follow us on Spotify and Apple Podcasts or whichever service you use, and check out the podcast homepage at the Cordis website. Subscribe to make sure the hottest research in EU's funded science isn't passing you by. And if you're enjoying listening, why not spread the word? We've talked about what baby baboons can tell us about language development. Listen to the episode on mind reading to find out more. In our last 43 episodes, there'll be something there to tweak your curiosity. The Cordis website has articles and interviews that explore the results of research being conducted in a very broad range of domains and subjects, from proteins to protons. There's something there for you. Maybe you're involved in a project or would like to apply for funding. Take a look at what others are doing in your domain. So come and check out the research that's revealing what makes our world tick. We're always happy to hear from you. Drop us a line. editorial@cordis.europa.eu. Until next time.